Hello, my name is Hector Gil-Marin. I'm a postdoc at the University of Barcelona, and today I'm going to be presenting the Redshift space distortion results from the eBOSS survey. So eBOSS is a galaxy survey, a Redshift galaxy survey, and it observes different kinds of galaxies, LRGs, ELGs, quasars, and also Lyman alpha lines. And in order to get cosmological information, what we do is to build up a three-dimensional field with the positions of all these galaxies and build up a overdensity field, delta. Delta is a stochastic field. So in order to get actually cosmological information from it, we need to build up this two-point function statistics. In configuration space, it's called the two-point correlation function, and in Fourier space, it's called the power spectrum. But both contains more or less the same amount of information. So the goal of measuring the correlation function of the power spectrum is to get cosmological information, and in particular, we are going to be using the BAO and RSD techniques. So from RSD, we get information on the growth of structure, or F sigma 8. And from the BAO peak positions, we can get information on different cosmological quantities, namely the BAO distances along and across the line of sight. This is DH and DM. So in particular, the BAO peak position in the isotropic signal constrains this specific combination, whereas the relative BAO peak position between the isotropic and isotropic signal, it contains this other combination. So the BAO is a standard ruler and is one of the cleanest probes to measure the expansion in the large-scale structure of the universe. It provides the expansion along and across the line of sight, but it requires previous knowledge on the horizon scales at recombination times, which we called rdrag in this talk. So one of the advantages of BAO is that the systematics are way below the statistical precisions of BOSS and eBOSS. So we don't really need to do many stuff in order to have a robust and strong BAO signal. The technique we use to extract cosmological information from the BAO peak, it's called the Alcock-Paczynski test. The cosmological principle assumes that the universe is isotropic and homogeneous. But when we transform redshift into distances, we need to assume a cosmology which in principle will be different from the true one. This produces a distortion on the BAO peak that we are actually able to measure. The measurement of the BAO along the line of sight is proportional to the Hubble function at that redshift. Whereas the measurement of the BAO across the line of sight is proportional to the angular diameter distance, which is the integrated Hubble function. We can define the scales factors Q parallel and Q perpendicular between the distorted and the observed wave vectors. These parameters depend, as we have seen before, on DH and DM. We can think of these two distortions along and across the line of sight as an isotropic dilation called dV, which moves the power of the power spectrum horizontally in the isotropic signal, and another distortion which would be a warping of the BAO between the longitudinal and the transverse scales. This one is what it's called the Alcock-Paczynski test, and it generates actually an anisotropic signal in addition to the isotropic signal of the BAO. The second distortion is actually proportional to the ratio between the DM and DH, which is the BAO scales along and across the line of sight. There is an additional effect we need to take into account on the BAO, which is the effect of the horizon scale. Large-scale structure is not very sensitive to the BAO scale recombination time. So because of this, we need to assume a reference fixed template when we perform our fit, both for BAO or RSD, that we call template cosmology. So for simplicity within eBOSS papers, we are going to keep this cosmology equal to the cosmology we have used before to transform redshift into distances. This template cosmology has an associated value for the horizon scale that we call rdrag fiducial. So when we fit our model to our data, we need to take this extra effect into account by defining alpha parallel and alpha perpendicular from the Q parallel and Q perpendicular by adding this extra factor of the ratios of the true and fiducial horizon scale. So as a consequence, it adds an extra factor to the isotropic BAO shift, but not to the transverse to the longitudinal BAO ratio, which is insensitive to this effect. When we transform redshift into comoving distances, we assume that the galaxies only move with the Hubble flow. However, galaxies also interact gravitationally among them. And as a consequence, a small component of their redshift is due to not only the Hubble flow, but to the peculiar velocities along the line of sight. So the effect that these peculiar velocities have in the infer position of galaxies is what is called redshift space distortions. Visually, the effect is to make the spherically symmetric structures squashed across the line of sight. And at small scales, they also generate the elongated structures along the line of sight that they are called fingers of God. The effect of redshift space distortions in the power spectrum or correlation function can be modeled because these peculiar velocities are actually coherent with the growth of the structure of the universe and with which is proportional to the amount of matter. So in these two images, in blue, we have what it looks like the actual position of the galaxies, and in green, what we actually observed by these contaminated peculiar velocities in the translation between redshift into comoving distances. So we take the simplest model as a toy model to explain the redshift space distortion, which is the Kaiser linear term. So redshift space distortions depend on the projection of the peculiar velocity along the line of sight. But in this sense, it maximally affects pairs of galaxies along the line of sight and does not affect pairs of galaxies which are transverse or across the line of sight. So one can define mu as the cosine of the angle between the line of sight and the pair vector of two galaxies. So the power spectrum will not only depend on the scale, but also depend on this extra parameter mu. So we expand this anisotropic power spectrum in the Legendre polynomial base. And what we find is that the coefficient of the first Legendre polynomial is what we call the monopole or the isotropic signal, whereas the first and the second anisotropic multiples are the quadrupole and the hexadecapole. Further multiples can also be computed, but they will have a very low signal to noise. So by measuring the monopole, quadrupole, and the hexadecapole, we can break the degeneracy and infer this parameter of interest, which is the growth of a structure F. So redshift space distortions end up boosting the power spectrum signal, unlike the Alcock-Paczynski, which was moving the signal left and right. But also as Alcock-Paczynski, it generates an anisotropic signal. So finally, what we call full shape analysis is the simultaneous fit of this growth of a structure F, alpha parallel and alpha perpendicular parameters that we have defined before, and these plus extra nuisance parameters such as the galaxy bias and stuff. So in this fit, we will have two effects, which is redshift space distortion that generates an isotropic signal and move the isotropic signal up and up. It boosts it, and Alcock-Paczynski, which what is basically move the scales through these alpha parallel and alpha perpendicular parameters left and right, and also generates an isotropic signal. And this is how it looks like when we infer parameters from by fitting simultaneously both using the full shape monopole and quadrupole in green in the right panel, and using the full shape monopole, quadrupole, and hexadecapole in red. So we see that by using the hexadecapole, it helps to break this degeneracy between the Redshift space distortion parameter F and the typically Alcock-Paczynski parameters alpha parallel and alpha perpendicular. The 2-point Redshift space distortions are not sensitive to the growth of structure alone, but to the growth of structure times sigma 8. Traditionally, what we do is to fit for F alone at a fixed arbitrary template and report the best fit F times the value of sigma 8 at that particular template. This presents a problem because sigma 8 is defined as the smooth power spectrum in spheres of 8 megaparsecs over h, where h is the h value corresponding to the cosmology of that arbitrary template and not the h value of the universe as it should be. So to make the F sigma 8 quantity independent of the true template, what we do is to rescale our template power spectrum by the best fit alpha 0 isotropic dilation scale. These corrections only turns out to be important if the chosen template cosmology has a best fit alpha 0 value very different from 1. Having said that, we fit the different samples, the LRGs, ELGs, and quasars in Fourier and configuration space using models which are a bit more complex than just the Kaiser linear term. Here I just list the ones we used. Basically, it's a TNS model in combination with some perturbation theory in Fourier space and some CLPT model, Gaussian streaming models in configuration space. Here are the results of the 2-point statistics for Fourier space and configuration space for the different samples, where the monopole is shown in blue, the quadrupole in red, and the hexadecapole in gray. So in order to do these fits, we have used the covariance computed from 1,000 realizations of EasyMox. But this study also uses the other syntactic catalogs based on full and body MOX, which are used for systematics, which are the outer rim plus some HODs models for the quasars, LRGs, and ELGs, plus N-series MOX for LRGs that they were used for the BOSS samples. So just as a very quick example of the systematics checks that we have done in order to put a systematic error budget on our measurements, here I'm just showing the potential dependence on the arbitrary template that we have used. So I'm just showing different templates, and I've just performed the full shape analysis using these different templates, which are shown in the plot on the right, and we are showing that the dependence on the infer parameters with this template are very small. There are also other tests that they were done using blind MOX, which were having different cosmologies, and they were all fitted with the same template. Here are shown the outputs, and you see that when we vary the cosmology, the model usually is able to account for this variation, and the small deviations are used to put numbers on the error budget that we are going to include in our final measurement. So just to conclude, just to say that SDSS2, BOSS, and eBOSS have provided direct measurements of DM, DH, and F sigma 8 in the redshift range from 0 to 3. And this is so far the largest spectroscopic galaxy survey, and is the current state-of-the-art measurements. And in terms of F sigma 8 precisions, here I'm just showing what eBOSS and BOSS have brought to these measurements. And you see that for most of them, they are about of 10% precision measurement, including the systematic error budget. On the panel, you see the different SDSS measurements in colors. And in green, there is this prediction by lambda CDM model using the Planck best fit measurements. So just to finish, I leave you here with the reference of the different papers that they belong to the eBOSS release. They are currently under examination by the referee, and hopefully they are going to be all public, and the likelihoods also available for public. That's all. That's the end of my talk. Thanks for watching, and hopefully see you in the discussion session. Bye.